Physics students, good afternoon. Mr. Fugit here. In this video today, we're going to be looking at an application of torque involving holding up a milk carton suspended by your arm. So this problem is geared towards number 12 on homework assignment 12, covering over torque and static equilibrium. So the problem statement reads like this. A cook holds a 1.88 kilogram carton of milk at arm's length. What force, FB, must be exerted by the biceps muscle? The acceleration of gravity is 9.8 meters per second squared, and ignore the weight of the forearm. So here in this problem, you're given a diagram to help kind of better give you a picture of what's going on. So I'm going to redraw the picture and an easy way to understand so we can get an idea of what all the numbers are we're dealing with. So at one end of our arm is where the milk carton is going to be held. Okay? At the other end of our arm is our elbow. Okay? So our milk carton is going to be over here on the left-hand side in what would be our hand. That milk carton has a mass of 1.88 kilograms. Now, gravity is going to be acting on that milk carton with a force. We'll say that that is a force of gravity. So I'm going to go ahead and calculate that force of gravity, just m times g. So 1.88 times 9.8 gives us 18.42. So this force is 42, not 24. 18.42 newtons, okay, just the mass of our milk carton times gravity. Now, okay, because that force is acting a certain distance away from our pivot point, okay, our arm forearm rotates around our elbow, pivots around there, it's going to create a torque. That torque is due to a force being applied at a certain distance away. Now, it's going to cause our elbow to rotate downward, what we would say is counterclockwise or a positive torque. Now, we're told that we also have a force from our bicep. Now, the picture looks a little bit strange, but we're told that FB, the force in our bicep, is a slight distance away from our elbow. So, I'm going to represent here FB, not Facebook, the force in our bicep. That's really what we're trying to figure out. How big does this force need to be in order to counteract or balance out the weight of the milk carton, right? So, we're told that that force is acting at an angle of 61.8 degrees. We have to pay close attention because that's not actually the angle that we're going to use here. So the last thing we'll do is that we'll take into account some of our distances. Okay? Now we're told the elbow is a distance of 8 centimeters from our bicep. I'm going to go ahead and convert that to meters, 0.08 meters. Just taking that value, converting it directly to meters. Now we're told that the milk carton is a certain distance away from our bicep. And the number I'm given is 25.9. So what I'm going to do is I'm going to add 8 centimeters to 25.9. So 8 plus 25.9 gives me 33.9. Now I'll convert that to meters. Just kind of do that in my head. And that's going to be, sorry, the picture's getting a little bit crowded. It can be very, very difficult and oftentimes pretty annoying when we're dealing with all these different numbers and distances. We want to label everything. So our pictures can get really, really crowded and clunky. So I'm sorry if it feels that way. Okay, but this distance is 0.339 meters or 33.9 centimeters away. So again, now that's kind of annoying, but I'm sorry, that's the best we can do. So we know a force and a distance. We know that since it's acting straight down, the angle will be 90 degrees, so we can forget the angle for the force of the milk carton, the force on the milk carton, excuse me. But we need to figure out the force in our elbow, or excuse me, the force in our bicep, meaning we need to look at the angle. Now this problem is trying to trick you by giving you the wrong angle. Well, not necessarily the wrong angle, but an angle not that we're going to use directly. So what we want to do is we want to find, well, the complementary part, or the other angle that would get us up to 90. This is 61.8. This is a right angle. So we need to subtract that from 90. And we're going to use actually 28.2. Because remember, when dealing with an angle, we want the angle between our distance and our force. And 28.2 is what's sandwiched there in between. So now what we're going to do is, in order for our arm to balance out the milk carton, we're going to set our sum of torques equal to 0. That's one of our conditions for static equilibrium. So we want to sum all the torques up, make sure that they equal 0. So let's start with the torque created by the milk carton. Well, we have a force of 18.4 newtons, and we're acting at a distance of 0.339 meters. So I'll just put that 0.339 in. This is our force of gravity on the milk carton. Force times distance, sine of our angle is 1, because it's at a 90-degree angle. Now, this is going to create a positive torque that's acting counterclockwise, so I'm going to leave it as positive. Now, this force in the bicep over here, you can imagine it's a little bit tricky, but if it pulls up and over our elbow, it's going to want to create a torque that is clockwise, right? And that makes sense because our milk carton creates a torque counterclockwise. We need the elbow of the bicep to create an opposite torque to balance things out. Because it's in the opposite or in the clockwise direction, I'm going to subtract this. So negative force in our bicep times its distance away, 0.08 meters, times sine of our angle, 28.2 degrees. And all that added together must sum up to 0. So now we're just going to plug in the things that we know. Well, our force of gravity was 18.42 newtons times 0.339 meters. I'm going to go ahead and multiply those together and make this a little bit simpler on us. So 18.42 times 0.339. It gives us about 6.24 Newton meters. And we'll subtract, well, our force in our bicep times 0.08 times sine of 28.2 degrees. That gives us about 0.0378 equal to 0. So now what we want to do is we want to get that FB by itself. Okay? So what I would do is I would move one of these values over. Doesn't matter which one we choose. We just want to get one to the other side so we can get FB by itself. So we'll just take our number, 6.24. I'm going to subtract this to the other side of our equation. And that's going to leave us with something that looks like this. Negative FB times 0.0378 is equal to negative 6.24. That's a torque, so it's in Newton meters. Again, when dealing with torque, it's important that we pay attention to our direction so we can make sure things give us the right direction when we solve mathematically. Now, to get FB by itself, well, you'll notice we have a negative on either side of our equation, so we can really cancel that out or divide it out. Ooh, excuse me. And I'm just going to go ahead and cancel that out because we know a negative on either side. And we can just cancel out, divide by -1, get rid of it. Then lastly, we're going to divide by 0.0378. So this value on the right-hand side will cancel out. And we'll get FB equal to, it's like about 165.2, I believe, newtons. Excuse me. So we'll double check our key. 165.2. Eureka, we have solved. Okay? So this problem is a little bit more challenging when dealing with the sum of torques because we are dealing with a force at an angle. So remember, things to keep in mind here, pay attention to our distances and their distance from our center of rotation, our elbow. Also, make sure we pay attention to our angle. We need the angle between our force and distance. And lastly, make sure we pay attention to our convention for the sign of torques. Clockwise would be negative, counterclockwise would be positive. If we don't do that, we're going to end up getting kind of a weird, maybe negative value even for our force in the bicep, which we know isn't going to be true. So, that being said, hopefully this gets you going on problem number 12. Don't hesitate to let me know if you have any questions. Good luck.